mentioned in previous weeks, we have a pizza lunch at the ITC about gravitational wave astrophysics. And actually this week's speaker on Wednesday, tomorrow, is Dan Dorazio. We'll talk about supermassive black holes as sources of gravitational waves. And then on Thursday we have Wednesday at 11 a.m., 11 to 11:45, and then at 11:45 to 12 there is a pizza served. So that is your reward for making the trip. And then on Thursday we have the ITC Colloquium at 11, also on gravitational wave astrophysics. From the perspective of a theorist, calculations using numerical relativity. And that is by Shoemaker. Dader, I don't know, how do you say it? Diege. Shoemaker is giving that talk. One last thing, tomorrow at 1 p.m., and that's not related to black holes, but just so that you know, because I think there will be a big splash of news reports about that. Very important discovery to be announced at 1 p.m. tomorrow at NASA. It has to do with the discovery, I've seen the paper, a discovery of 7 planets around a dwarf star that is 8% the mass of the Sun. At least 3 of them are just at the place where you expect them to have oceans. They have properties and surface temperatures probably that allow oceans to exist on their surface. So it's one system of 7 planets around a single star. Quite remarkable, and they are transiting. That's the other thing. So the fact that they are going in front of the star will allow us in the future to infer the composition of their atmospheres, potentially finding evidence for oxygen or other indicators of life. That's the first time that we have such a system where a transiting planet has a mass similar to the Earth, in this case several of them, in the habitable zone of the star. And by the way, such a star lives for up to 10 trillion years. A star that is roughly 10% of the mass of the Sun can live 1,000 times longer than the Sun. So another big advantage to be there, other than living on the surface, on the edge of a beautiful ocean, is the fact that this star will survive for much longer than the Sun. Check out the NASA website at 1 p.m. tomorrow.
Good afternoon, everyone. Great pleasure to introduce our first speaker today, Nishanth Gudapati, who's visiting us from Yale University, where he is now a postdoctoral research fellow. So Nishanth got his PhD from the Albert Einstein Institute in Germany, and he then went on to do a postdoctoral stint at Johns Hopkins University before joining Yale. And today he's going to share with us some exciting results about linear stability of the Kerr-Newman spacetimes.
Thank you very much. Thank you to Aruna for the invitation as well, and also to Professor Yao. And thank you all also for coming. Yes, so I'm going to talk about a mathematical problem that has been sort of very popular throughout the mathematical or theoretical studies of Einstein's equations for general relativity. They've been popular on and off, but somehow have somehow always made a comeback in terms of the interest of the community. So I'll state what the problem is and what that's about. But before I do that, let me briefly go through the outline of the talk. The stability and the black holes that we are interested in are the so-called Kerr-Newman family of black hole solutions. Of course, when we say black holes, we basically implying that we know the global structure of the solution of the Einstein's equations. So that's a kind of a global problem. So anyway, so I'll discuss the geometry of the Kerr-Newman family of black holes. I'll discuss what the stability problem is, and I'll discuss the specific results that we obtained recently. The work is still unpublished. It's not on the archive yet, but it will be up in a few weeks' time. So the title suggests this work is concerning the stability of the Einstein-Maxwell perturbations. But since perhaps you know, the Einstein's equations are very, very technical, so for a 30-minute talk, I thought it's better to discuss more on the Maxwell perturbations of Kerr. The idea is that the essential ideas of the proof are kind of similar. Many of the difficulties that you will see for the Einstein-Maxwell problem, you will see also for the pure Maxwell perturbations of Kerr. But also, of course, I'll say what the final results, and I'll also discuss the final statement of the Einstein-Maxwell case. Anyway,
what about just a scalar? Is that somehow
Sorry?
different? What about just a massless scalar? Is that qualitatively different?
In some sense different, yes. And that's also one of the modal problems, that's right. So if we perturb it just with a scalar field, especially in the axial symmetry case, it will result in a drastic simplification. I'll discuss that, I'll mention. With the Maxwell case, with the vector field, that simplification doesn't work, so for example. So that's sort of the whole idea here. So anyway, so let me, one small thing that I want to mention at the start is that in this talk, sometimes I might flash some really elaborate formulas and stuff, but the point is, of course, not to make you suffer or anything. It's just that I just want to you to get a feeling of what's going on, but I'll explain immediately what the essence of those formulas are. Please don't be too concerned about. Please don't be too alarmed if you see long formulas like that. Anyway, so what's the point? We are looking at a family of solutions of Einstein's equations called the Kerr-Newman family of solutions, which are a 3-parameter family of solutions, the parameters being the charge, angular momentum, and the mass. A is the the specific angular momentum, Q is the charge, and M is the mass. It's a solution of the Einstein-Maxwell equations of general relativity, where I absorb the cosmological constant into the energy momentum tensor here, and it's considered to be a very important solution. Probably, in general, the Kerr family is considered to be perhaps one of the most important solutions of all solutions of Einstein's equations. Why is that? I'll discuss in a moment. One quick observation about the metric form is that it has 2 killing vector fields, the dt and d phi killing vector fields, and as I said, it denotes the space-time represents a massive charged rotating black hole. And why is it an important solution of Einstein's equations? It's expected that all the black hole solutions, all the asymptotically flat black hole solutions, eventually become a member of the family of the Kerr-Newman solutions. Yes, and of course, by the asymptotic steady state, by that we automatically mean that it's going to be a stationary solution, of course. To be more technical, there are some assumptions on the regularity on the horizon and so on and so forth, but the basic point is that it is expected that all black hole solutions within the class of Einstein-Maxwell equations eventually converge to the Kerr-Newman family. Just before we move on to the next slide, a couple of important properties of the Kerr-Newman black holes is, of course, that you have a horizon, the event horizon, which is perhaps but let me say that the part of the space-time that is not visible from null infinity is called the black hole space-time, and the boundary of that region is the so-called event horizon, and it is given by the upper root of the delta function that's part of the metric in the previous slide. Another very interesting and very important property, very critical property for our talk here and in general, is the so-called ergoregion. So you see the dt killing vector field, it's a killing vector field, all right, but it is not time-like in all regions of the space-time. It becomes null-like on the boundary of the ergoregion, and it becomes space-like within the ergoregion, and it introduces many complications in terms of the mathematical study of the stability of these systems. Of course, it also results in many physical effects. Perhaps you've heard that there's this effect called frame dragging, where a particle cannot remain stationary if it's within the vicinity of a rotating object. In particular, the frame dragging effects of the Kerr family of black holes within the ergoregion are quite strong. And one effect of that is that another interesting thing that happens with the ergoregion is that you can extract the energy out of the angular momentum of the black hole. That's called the Pancoast process. Perhaps you've heard about all these things. I just wanted to be complete. But this ergoregion is going to be very important. I'll discuss more about that later. It plays an important role from the mathematical perspective as well with regards to the stability problem. Anyway, so what is the stability problem? What's the formal statement of the stability problem? What is the problem that we're working on? Of course, the precise statement of what we would like to understand is something that's a little bit vague, but roughly speaking, what we're saying is that you have Einstein's equations and you have the space of solutions of Einstein's equations. Among that, in that space, one point is the Kerr-Newman family, and what you're basically saying that all the solutions near that Kerr-Newman family asymptotically converge to a member of the Kerr-Newman family. Basically, if you perturb it within the space of solutions, if you perturb the Kerr-Newman family and evolve it, and if you evolve it long enough, it converges into another member of the Kerr-Newman family. Okay, so in all of these statements, you can remove the word Maxwell and the word Newman and say the same statement for the Kerr family as well, for the vacuum solutions. Okay, so that's a formal statement of theorem that we're working on. Sorry?
Do you want a then before the maximal development?
Sorry, what? I don't understand the question.
Well, I'm just a little confused about what you're saying here. Isn't it shouldn't the perturbations decay to zero? What does it mean to say that the perturbations
No, they don't decay to zero.
What does it mean to say that they decay to a member of the Kerr-Newman family?
You might change the angular momentum.
I mean,
You're fixing a background geometry.
Isn't it the
You're
maximal
not
development?
including back
It's the
reaction,
maximal
right?
development that decays, not the perturbations.
I mean, it doesn't decay exactly to the same. For example, it's expected that the final mass of the black hole would be different from the initial mass. So it will not be the exact same statement. Yeah. I mean, all I'm saying is what I said in words is that we have a solution of Einstein's equations and we perturb it, and the idea is that it converges to another member of the family if we evolve it long enough. So that's all I wanted to say there. So, as I said, the precise statement, it's a little bit unclear what hidden behind those are many deep questions with regards to Einstein's equations, like cosmic censorship and what we would like, what would be the null infinity of this maximal development, and what about the black hole of that, and so on and so forth. So, like all of these cosmic censorship conjectures and so on are hidden behind this statement. So yeah, so I didn't try to
So
make
this isn't supposed to be a well-posed mathematical statement.
not quite, no. Yeah, part of the conjecture is to sort of find what the conjecture is, so to speak. So.
I mean, don't you need a norm to know whether it's
Yes,
far
all of
away
the,
from?
yes, exactly. I mean, as I said, this is only a paraphrase of the actual problem. So,
Okay.
and how do we, for example, how do we characterize that it's another member of the Kerr family, for example? That's another big question, and so on and so forth. So.
I mean, is this true for flat space, for the trivial case?
Yes, yes. In this famous work of Christopher Pannerman and so on.
Right, but they had a very non-obvious norm, right? So
Yes, and there was another work. So that they work at the level of curvature. That's right, but they perturb it, and they work at the level of their estimates work at the level of curvature. But there's another work by Lindblad and Rodniansky where they work at the level of the metric functions. So they're different versions of it. As I said at the start, it's a rough statement, and it's basically the solution of a PDE, and we're trying to find whether that solution is stable within the class of the PD or not. So it's essentially that's all I wanted to convey with that statement there. So okay, so anyway, so let me discuss what the problems are with regards to the stability statement. So there are some very important results with regards to the modal stability. But if one goes beyond the modal stability, one of the as it was mentioned, one of the really important results with regards to the stability of any solution of Einstein's equations is the Kerr-Newman result, where they proved the stability of the Minkowski space, and there's an extension of that in this nice book of Bieri and Zipser, where they extend that with regards to the Einstein-Maxwell perturbations, and they also prove stability. As I said, it's a problem. Eventually, it boils down to a problem in PDE. How do we solve that stability problem? It basically comes, the techniques basically come from the techniques that are mainly motivated from partial differential equations point of view. And one of the important techniques that they use is that they first linearize the field equations around the solution, in their case, around the Minkowski space, and they use the background symmetries to construct higher order conservation laws and exploit that to prove the decay for the linearized field equations, and also eventually prove the decay for the nonlinear fields as well. So the basic advantage that one has is that we have a lot of symmetries of the Minkowski space. That's one good thing. And the second thing is that the energies either are manifestly positive definite or can be dominated by the energy that are manifestly positive definite. That's one thing. And secondly, of course, they also use the conformal symmetries of the Minkowski space to prove the stability. One of the really big problems for Kerr is that argument doesn't work, because the energy of even the linear wave equations, if we have a linear wave equation, as I said, we just have the wave equation perturbation of Kerr. Just take an equation that is as simple as that. The energy of the linear wave equations is not positive definite. Is not necessarily positive definite. It has an ambiguous sign, and that is because of the ergoregion. Right. So how do we calculate the energy? Basically mean. So we have the energy momentum tensor associated to that, and we contract that with the timeline Killing vector field, and since it's a Killing vector field, it gives a conservation law, and it's till that stage it's quite good. But the point is that it doesn't have a sign. If it doesn't have a sign, then it cannot be used for the PDE techniques. It's not the end of the day, but it causes many big problems in terms of a PDE technique point of view, to be able to prove questions like boundedness or asymptotic decay of the fields. So there have been many works which overcame that difficulty, and people have been working on the model problems associated to that stability. Many interesting deep works from different perspectives came about in the context of these model problems. So one strategy to deal with that ambiguous sign of the energy is that you introduce another. So these dt and d phi are both the Killing vector fields, but you introduce a certain weighted vector field which compensates for the loss of the ambiguity in the sign. But the problem is that it's not conserved, because this chi depends on, it's not a constant, it's a function. So therefore, when you calculate the divergence of the contraction of the energy momentum tensor with that vector field, you'll see that it's not doesn't give a conservation law. So, for example, so you have positivity, but you don't have the conservation law, and that works mainly for small angular momentum. So there are many issues like that that one would have to overcome when one is understanding the question of uniform boundedness even. Yes.
So is it correct that the linear problem of stability has been solved, but only in the last 5 years or something? Is that, or is there still open problems?
Yes. So the linear I don't know what you mean by linear waves. Linear
Yeah, linear waves.
Yes. That's a comprehensive understanding of the linear problem for the full sub-extremal range. This is for small angular momentum.
Yeah.
For the full sub-extremal range has been resolved by this work of Daffermos, Rodniansky, and Rothman very recently. Yes. So with full generality. Yes. So there have been many works. For example, many of these works, for example, assume small angular momentum, and if you do that, there have been also pretty strong results in that setting as well. So. With full generality, I think it's been resolved only very recently. Yeah, even as you see, even last year. So it was published last year. It was, I think, resolved in the last 3 years or something.
So I guess what you're saying is that now that the linear problem has been nailed, it's time to start thinking about the nonlinear one. Is that?
No. So this is a linear wave equation,
Yeah.
but a linear scalar wave equation. But the same things do not hold. For example, if you consider even linear. Not necessarily scalar waves, but like Maxwell fields, for example. Even that is not known.
So how can you hope to think about the nonlinear problem, which you mentioned on the previous transparency?
Yeah, I mean that's a problem for that's maybe could be resolved in like maybe 20 years or something. So that's a general.
You're not working on it now.
I'm not working on it now. I'm working on the linearized version of that problem. Yes. That's why I said I was not trying to be very careful with that statement. Exactly what that's supposed to mean. So there are some charges. Yes, please.
So even for the non-scalar linear waves, are there results? Does the spin matter? So are there results in low spin, and you're going to talk about all the spins?
Yes. So for example, for the spin one fields for the Maxwell, we do not know much about the behavior of the fields. For rapidly rotating black holes, for angular momentum which is not necessarily small. But we obtained some results about that, and that's what I'm presenting. So the idea is that the construction that we're presenting here holds for the full sub-extremal range if you assume axial symmetry of the perturbations. If you assume axial symmetry for the linear wave equation, the whole problem with the sign drops out. So you have positive definite energy for that, because the term that gives the ambiguous sign basically becomes 0. Because if you assume axial symmetry for the linear wave equation, but that doesn't work for example, for the Maxwell fields. So that simplification doesn't work. So anyway, so there are many very interesting deep works in that direction. In this talk, I will quickly move on to the actual content. So we'll be considering the Maxwell perturbations of Kerr, but we'll be restricting to the actual symmetry. And we'll be using the Hamiltonian formulation of the initial value problem. Once we do that, the variational principle that gives us the Hamiltonian equation, of course, the Maxwell equations also have their own constraints. And the nice variational principle that gives the Hamiltonian equations for the Maxwell fields propagating on any curved space-time is given by that. If you perform the variation with respect to AIs, for example, we get the curved space equivalent of the Ampere's law, and N and Ni's are not the canonical variables, but A naught is, and if you perform the variation with respect to that, we'll get the Maxwell constraint equation. So that's a nice variational principle that captures all of the Hamiltonian equation. It's given, for example, in MTW in the chapter 21. And if we do that, let me state the final theorem that we were able to obtain, which basically says that there exists an energy for Maxwell's equations propagating on the Kerr space-time that is positive definite and conserved, and strictly conserved. Okay, so how does it work? It works because in actual symmetry, the Einstein's equations, the Einstein-Maxwell equations, have a very beautiful, mathematically very beautiful structure that can be exploited to come up with some identities that will solve this positivity problem, actually, as I shall describe later. So what is that mathematical structure that Einstein's equations or Einstein-Maxwell's equations admit when you have actual symmetry? It is this so-called twist potential formalism. So you can introduce, instead of working with the vector potential, you can work on the so-called twist potentials defined as follows. And there's a geometric meaning of what those twist potentials are. I'll try to describe that towards the end. They're part of a map and so on and so forth. But anyway, so if we introduce those variables and rewrite our Hamiltonian energy in terms of those variables, and also the Kerr metric can be transformed into a certain geometric structure called a wave map. Perhaps you're familiar with that. For example, if using the times translation Killing vector field, you can also construct a harmonic map of the Kerr metric. They're called the Ernst equations and so on and so forth. Perhaps you've heard about that before. It's a similar kind of a structure, but here we're constructing the actual symmetry. And we also introduce a certain twist potential that's called the gravitational twist potential associated to that. In those variables, you can transform your Hamiltonian energy, which looks like the following, but the problem still doesn't solve. You just rewrote the problem in terms of different variables. You see this sign, this term, for example, has an ambiguous sign. So that's the problem term there. Right, but we can play a little trick here, which I shall explain in a moment's time, which is,
Sorry, where is the ambiguous sign?
this term. So this whole term doesn't have a sign, right? So it's all of these are contracted by, it's like the norm squared, and norm squared, but this term doesn't have it. The small trick, and that has very curiously a very far-reaching generalization. You don't have to restrict to pure Maxwell, you can restrict to full Einstein-Maxwell perturbations of the Kerr-Newman spacetime. Anyway, if I, for example, was discussing the formula equivalent to that, it will take like 3 slides, so that's why I chose to discuss the pure Maxwell perturbations first. Anyway, before I discuss about that trick, let me mathematically formulate what the initial value problem is. Of course, the Maxwell equations are hyperbolic, second-order hyperbolic system of partial differential equations. You can see that, for example, in the Lorentz gauge for the vector potential. But here, in terms of the twist potentials, you can also see that they're second-order hyperbolic linear wave equations, and you specify the initial data. And by the very fact that we are assuming the existence of those twist potentials, means that the Maxwell constraint equations are automatically satisfied, so you don't have to solve for them. And these sort of wave map equations for the background that I discussed are the following. They play an important role in the identity that I'll discuss soon. So anyway, if you remember, this is the problem term in the Hamiltonian that we discussed, in particular this term. What you can do is you can use the background field equations and roughly come up with an identity like that, where what you're basically doing is that because this term is problematic, you try to absorb these e to the gamma terms inside and come up with a transformation that has a very exactly what we need. It transforms into a positive definite part plus divergence terms. If you impose the background field equations, as I said, for this identity to hold in itself, you need some terms where you have some background field equations.
You're assuming this is all happening on background Kerr. In some sense or other, you're assuming that these Maxwell fields are small, but I have no idea what it means to say that a Faraday tensor is small. I don't know what a natural norm on the space of Faraday tensors is, or on the space of Spacetimes tensors. So, what is the justification for saying that at this Maxwell field you're assuming is small enough that we can ignore the contributions to the metric?
That's a good question. when we say, how do we measure this small, when we are discussing the perturbation theory, how do we measure this smallness? For the linearized theory, if you consider a one parameter family of solutions, you parameterize your solution in terms of, let's say, S. You calculate the derivative with respect to S, basically the Fréchet derivative of the function that I discussed, or the gravitational functional in the most general case. There you will see you basically calculate the Fréchet derivative at the Kerr-Newman spacetime, and then once you plug in that, you will see that the metric perturbations and the Maxwell perturbations are decoupled. Actually, I think I wrote about something about that somewhere. Yeah, so the metric perturbations and the Maxwell perturbations are decoupled. So therefore, without disturbing the Maxwell's equations, you can basically turn off, as a special case, turn off the metric perturbations.
Right, but if
At the first order.
that does me no good. If I have just some enormous Maxwell field, in some sense of enormous, turning off the interaction is physically unreasonable. So I want to know what the justification
Physically,
is.
yes. So as I said, the reason why I chose to turn off is because of mathematical simplicity and presentation. But you don't have to turn it off. The final formula that I'm going to give of the Hamiltonian is for the full coupled perturbation problem. So there's no such restriction. The restriction is only artificial that I chose for presentation purposes. Yeah.
Are your twist potentials functions of all variables?
That's a good point. So
Or
the
only
twist, something that I should have mentioned. So the twist potentials come when you have the actual symmetry, right? So when you do the dimensional reduction to the lower dimension, take the quotient, twist potential live on that quotient basically.
So you drop the T phi dependence? Or
It will have T dependence, but it will not have phi dependence. Yeah.
yes.
Anyway, so you can use this transformation and convert that into a positive definite quantity plus divergence terms, and these divergence terms become zero if you choose an appropriate perturbation, like asymptotic flat perturbation, and if you choose, for example, that they vanish on the horizon. If you at some point I'll draw the Penrose diagram. If you choose the perturbations which are, for example, compactly supported, then it will not have any contribution either at I0. By the way, so we're in the foliations that are locked down at the horizon. Maybe I should draw that. So we are looking at perturbations of this kind here, like that. So this is the R plus, this is the I0, and this is the bifurcation 2 sphere. So if you start with the compactly supported perturbation like that, it stays compact, right? So therefore, the flux terms at I0 and sphere and the horizon, they're zero. So therefore, what you have is a positive Hamiltonian. But the positive Hamiltonian is again not good enough if it's not conserved. But later we prove that actually is a conserved quantity. Since the time is short, let me just mention one thing, that this Hamiltonian that we construct has seemingly a degeneracy on the horizon. It means that it has terms in the energy density, has terms in the integrand which go to zero, but that's only sort of a superficial thing. If you introduce the renormalized variables, you can convert the Hamiltonian into a nice non-degenerate form, at least the H1 type energy. So anyway, since the time is short, let me quickly move on to the general perturbation problem, where the same thing holds if you consider the whole coupled Einstein-Maxwell perturbation within the actual symmetry of the Kerr-Newman spacetime. You can also construct, if you start with the ADM variational principle of the Hamiltonian of the full Einstein-Maxwell system, and if you calculate again its Fréchet derivative and use this transformation, and later, of course, it's not so. There are many pedantic technical issues that are perhaps not useful to discuss. But anyway, the same positivity holds. That's the key point there, and that's the final energy that we have for that particular case, where so all of these positive, and this is a time coordinate gauge term which you can choose. For example, if you choose maximal slicing, 2 plus 1 maximal slicing, this whole term drops out, and therefore you have a manifestly positive definite form of the perturbed Hamiltonian. and where VI's are, those one forms which are given by the following. So it's the logic is essentially similar, but there are many technical issues. For example, to prove that your Hamiltonian converges, you need to assume that the fall-off conditions are such that the ADM mass converges. But once you do that, you'll have to prove that the asymptotic flatness conditions are preserved through the time, and so on and so forth. There are many technical issues that I won't go through. Somebody else in the questions time, I'll discuss that. Just before I finish, let me say that some of these techniques are motivated from the earlier work of Moncrief on the coupled Einstein-Maxwell perturbations of Rice-Nordstrom spacetimes, and the advantage of post-definite energy is that now one can use the symmetries. One can go back to this, for example, the Christodoulou-Kleinerman philosophy of using the background symmetries of the space-time and use these commutator estimates to prove uniform boundedness and decay of the fields. It's a work in progress. I would like to mention that there's another very interesting series of works by the Chicago group by Wald, who are trying to prove the positivity of a certain perturbed Hamiltonian for the Kerr space-times using significantly different formulation based on the Hertz potentials and Tucholsky formalism. We would also like to mention there's another very interesting work by Dane and the Austria where they proved the positivity of a certain mass functional for the extremal case for Kerr. The final statement I want to make is that perhaps you've heard about before, there are many very beautiful highly technical techniques, for example, coming from micro-local analysis and so on and so forth, which are able to cope with the difficulties caused by the ergoregion. But the advantage of this energy is that it sort of reduces to this good old-fashioned, energy estimates to prove the stability. So that's the final statement I want to make. Thank you.
So maybe we have time just for one quick question.
So there is one part of the Kerr solution, which is the singularity, that is quite problematic. It signals the breakdown of the theory. So
Yes.
So I guess you are avoiding that.
Yes. When I said that, I wrote the word exterior of the. When mathematicians, all of us, when working on the stability problems, we basically mean the exterior, the DOC of the Kerr is stable.
And do we know anything when we get close to the singularity?
There are many very deep conjectures. Again, perhaps you heard this BKL kind of philosophy. The inside the horizon, the solutions are expected to behave similar to the cosmological solutions somehow, and therefore they are expected to have this chaotic behavior and eventually converge to the singularities. That's one of the another big open problems in mathematical general relativity. Again, which involves really heavy mathematical machinery and so on and so forth.
So there are people focusing on the...
There are some people focusing on... I don't know if there are too many people focusing in the context of the black hole stability, but there are certainly in the context of some cosmological solutions, people have been working on this BKL kind of stuff. So generally, when as it was pointed out, we're so far away even to answering in some questions in the exterior that somehow that question that too many people have been thinking about. There have been some people thinking about with regards to the stability of the Cauchy horizon, where another root of the delta function there is this so-called Cauchy horizon, R minus here, which is also sort of inside the event horizon. And some people have been thinking about that. I think the next speaker, Jonathan Luck, has worked on that a little bit, so maybe he'll be able to answer that. But I'm not sure if anything is conjectured about the behavior close to the singularity in concrete matters.
One quick one.
Oh my goodness.
You don't
Please
mind.
go ahead.
So, you've been talking about stability.
Yes.
So suppose the system is not stable.
Yes.
What is the expectation?
So that's a very good question. So one may ask, we have been observing black holes, now we observe that, so we're in a very good situation now. We know that black holes do exist, they are for real. But if they're not solutions, if these solutions are not stable, then that's a sort of very deep problem in the sense that there is some problem with the Einstein's equations that its black hole solutions are not stable, but there exists maybe some other black holes or some other solutions which are stable and that we are observing. So it means that the black holes that we're observing are not Einsteinian black holes.
Yeah, but I'm just thinking, physically, we already know the black hole solution has got this singularity.
Yes.
And now if we say it's unstable, it has to do something. And the singularity is not going to go away. So I'm just trying to visualize, what does this unstable...
If it's
space
unstable,
time do?
the point is it will sort of, it's unstable basically means that it will go away, so to speak. It's not for real. It's like some...
The singularity can't go away.
No, but it will be surrounded by something else.
Something else, what?
The event horizon will vanish and have a naked singularity.
Naked singularity. Okay.
Yes.
That's one possible solution.
Yes.
So that's what we are talking
Or a
about.
white hole.
Okay, so let's
Yes.
thank Nishanth. And I want to point out that Nishanth is with us till tomorrow afternoon, so if you want more discussions, he'll be around and he has an office space here on this floor. So
That too.
thanks.
Does that mean they couldn't have formed in the first place?
There can be transients and
Yeah.
Yeah, they can be,
an intermediate step. Like stars are an intermediate step in the evolution towards something.
Is there a way to estimate how much time it
Well, if it's unstable, then cool problem.
Joshi has constructed a family of solutions that are basically black holes, but are unstable in the sense that basically just throwing in the tiniest bit of matter will make the event horizon vanish and make the singularity.
Is there a time, a time scale?
No, you assume the completion of perturbed up until the time that you hit it with a stick. And then it vanish.
Instantly?
It's cut off. It sometimes happens, that's why. This one? It's very strange, sometimes it has, apologies everyone, it's decided to reformat. I have no idea.
It's not using the full screen, but it's
I
okay.
know, it's cutting off the top and bottom. Okay. Oh, let's try that. Just want it to not. Let's see.
Oh, that's
Oh no,
worse.
it's okay. Wait.
Make it smaller.
I think if I do this. There we go. Okay.
Great.
Apologies for the delay.
Great, well, I'm delighted to introduce our next speaker, Anna. I'm
Thank
so
you.
sorry. Anna Pancoast. So Anna and I were actually grad students together at UCSB, where we had an Anna and Anna. And I've been confused ever since, clearly. Anyway, so Anna is an Einstein Fellow at the CFA, so she's a local, and today she's going to tell us about measuring black hole masses using a really exciting technique called that I can never pronounce, reverberation mapping.
Thank you, Michael. Hello, everyone. It's a real pleasure to be here. So, as Michael said, I'm going to talk about how we can actually measure the mass of astrophysical supermassive black holes using light echoes, which is, in a sense, what reverberation mapping comes down to. And this is work I've been doing in collaboration with a number of people, chief among them being Catherine Greer, Michael Fosna, and Peter Williams, who are all postdocs and graduate students. But I also have to point out the contribution of the large number of astronomers that came together to gather the reverberation mapping data sets I have listed here. This is truly a group effort and is well over 100 different people. Okay, so, I don't have to motivate to you guys why we need to study supermassive black holes in practice. But unlike Chungpei Ma's talk at the beginning of the year, where she talked about measuring supermassive black hole masses in the local universe by spatially resolving the motions of gas or stars close to the black hole, I'm going to talk about a completely different approach, which we can use farther away, outside the local universe, which depends upon supermassive black holes that are actively accreting in active galactic nuclei, or AGN. And the picture that we have for this is, do we have the pointer thing somewhere? Oh yeah, thank you. Is that we have the supermassive black hole in the center, and it's surrounded by this accretion disk, which is emitting in UV and optical photons. And around the accretion disk, we have this region called the broadline region. And it's called this because gas in this region is moving so quickly around the black hole that the emission lines from this gas are actually broadened. And just to be completely, to finish this picture, around the broadline region we think there's this obscuring dusty torus, which actually blocks our view of the broadline region in certain sources when you're trying to sort of look from this direction. To give you some scale, we're talking about a region that's about 10 to the 4 to 10 to the 5 gravitational radii away from the supermassive black hole, although this depends a lot because the broadline region size not only depends upon the black hole mass, but also on the AGN luminosity, how luminous the accretion disk is. And the reason why this region is so important is that it allows us to substitute time resolution for spatial resolution so that we can still resolve the motions of gas deep within the gravitational potential at arbitrarily large distances from us. So how does this actually work? How do we use the broadline region to measure supermassive black hole masses? Well, we use the width of the broad emission line as a measurement of the velocity of this gas in the region, and then we combine it with a size of the broadline region, or a distance of this gas from the supermassive black hole. And the way that we get this second measurement, the size of the broadline region, is by using light echoes through reverberation mapping. And the way reverberation mapping works is you have this accretion disk at the center, and the accretion disk is actually stochastically variable in time, the flux that you measure, okay? And so if you can monitor an AGN and look at either the ionizing photons, or if that's too difficult to observe, you could look at the optical photons, which people have found to sort of track very closely the variability of the ionizing photons. And then you look at ionizing photons that have been reprocessed as broadline region flux, you'll see the same variability features in the ionizing photons as you see in the broadline flux, but with this time delay that's due to this extra light travel time. And so that allows you to measure a time lag and thus a sort of size of this region. So to show you some actual data.
Wait, but there is an implicit assumption that the velocity that you measure is related to is induced by gravity. Square root of gm over r.
That's right.
Because in principle it could be pushed by radiation pressure.
Absolutely, absolutely. And unfortunately, radiation pressure specifically is the same radial dependence. So you wouldn't be able to differentiate between radiation pressure and the black hole mass. So everything I'm going to talk about is assuming a fairly simple picture, but it is basically what allows us to measure black hole masses outside the local universe. So let's all hope that it's a pretty good assumption. Okay, so to show you some actual data, most of the work that has gone into reverberation mapping has focused on the optical, because that's sort of the easiest to look at from the ground especially. And this is the part of the spectrum that is also most often used. So we have H beta, which is this broad emission line here, and we have some narrow O3 lines here, which are very helpful because they do not vary, and so they're useful for relative flux calibration between spectra. But you can see there's a lot of other things going on. We have broad helium-2 and broad iron-2, which are also generated in the broadline region, but in different regions. So a first-order step is just to try to isolate the broadline flux of interest. Then we can integrate that flux and generate broadline flux light curves and cross-correlate them with variations from the accretion disk, usually in the optical, and use that to measure an average time lag. So this is sort of traditional reverberation mapping as it has been done. And to go from this picture of generating a lag from two light curves to an actual black hole mass, we combine it with the width of the broad emission line, multiply by c to get a distance, divide by g, and the final piece is that we have to normalize this black hole mass because there are all these details, such as the geometry, dynamics, and orientation of the broadline region that have to be taken into account. And unfortunately, because we cannot spatially resolve the broadline region, we don't really know what these should be. And so, trying to figure out what this value of f is becomes one of our biggest challenges. So currently what is done is to measure an average value for the entire reverberation map sample using this relationship between supermassive black hole mass and stellar velocity dispersion of the host galaxy bulge. This was a relationship found for local supermassive black holes, measured where the masses were measured from gas or star dynamics, where we could spatially resolve the gravitational sphere of influence. And we assumed that the reverberation mapped AGNs should have the same relationship. And if you make that assumption, you can get an average value of f for the full reverberation mapped sample. Unfortunately, that also ends up introducing a fairly large uncertainty in any individual black hole mass measurement that could be as large as the scatter in this relationship, which is about 0.4 dex, or a factor of 2.5. So, just to put this in context, this is a large uncertainty to be carrying around with your most precise method of measuring black hole masses outside the local universe.
What's the value of f that you get?
So I think it's about maybe in logs, it's about 0.74.
Close to 1.
It's about 1, yeah. Okay. So because reverberation mapping is so time intensive, you have to monitor an AGN for many months or longer, and you have to be lucky in that it will vary because AGN are stochastically variable. This technique has actually only been applied to about 60 different objects. But out of that, we've actually gotten a very powerful technique that has allowed us to measure black hole masses in AGN and quasars at any redshift. And that is this relationship between the size of the broadline region, specifically for this line h beta that I keep showing you, and the AGN luminosity. Okay, so you'll see this is a very tight correlation with a scatter of only about 0.16 dex. Okay, and this means you can all of a sudden take a single spectrum of an AGN, measure the width of the broad emission line to get the velocity, and measure the AGN luminosity to get a size for the broadline region, and use that single spectrum to get a black hole mass. But not only do you have to make a number of assumptions about the fact that this relationship should be even valid outside of the sort of local reverberation map sample, but you also still have this large uncertainty from not knowing what's going on in the broadline region. So what I'm going to talk about for the rest of my talk is not necessarily about measuring black hole masses. That's certainly very relevant. But how we get to measuring more precise black hole mass measurements, I think, comes down to understanding what's going on in the gas in this region. And the approach I'm going to take is by trying to model the highest quality reverberation mapping data sets I can get my hands on, and try to quantitatively constrain the structure of the broadline region, being able to measure this normalization factor f in individual sources, and hopefully in the process of this, having black hole mass measurements that you can get with less than 0.4 dex uncertainty. So that's going to be the goal. And before I get into the results, I just want to tell you a little bit more about the actual method that we use. So the idea is that we're going to try to model the distribution of broadline emission. You could also think about trying to model the distribution of gas in the broadline region, but going between gas and emission, you have to include a bunch of complicated photoionization physics, which is a goal. So we started off by just trying to model the distribution of emission. And the idea was that we would take our AGN continuum light curve that comes from the accretion disk at the origin and filter it through some distribution of point particles. And each point particle in our model is simply going to act like a mirror, and it's going to reflect the photons from the accretion disk to an observer with a time lag that depends upon a point particle's position, and a wavelength shift in the emitted line flux that depends upon the point particle's velocity. So once you have some distribution of point particles and you filter through a continuum light curve, you can generate a time series of emission line profiles that can be directly compared to real data. So then one of the challenges becomes, how do you assign all the positions and velocities to these different point particles? And that comes down to a choice of how you're going to model the broadline region. But ideally you'd really like to be able to match real reverberation mapping data, both the spectral line profile shape as shown here and the integrated line flux. So the place that we started was by trying to develop a simply parameterized phenomenological model for the broadline region that made as few assumptions about what was going on in the broadline region as possible. So we allow it to be a thin disk to a sphere, This, can be viewed at an inclination angle, including an edge-on inclination angle, even though we think that's unlikely because those should be sort of hidden behind a dusty obscuring torus. We allow for a transparent to opaque midplane, more emission from the near or far side of the disk, and you can think of that as being whether the gas is re-emitting its line flux back towards the central ionizing source or away from it, and more emission in the edges of the disk, so you could go to sort of a cone-like geometry. And then the dynamics are a combination of either near circular elliptical orbits plus either inflowing or outflowing orbits. Okay, so now I want to actually show you what we get when we apply this simple model to real reverberation mapping data. So the first data set that we applied it to was the Lick AGN Monitoring Project 2008 data set. And so 5 of the objects in this sample were variable enough for us to try to model the reverberation mapping data. And what we found was that the H-beta emitting geometry was close to face on thick disks. And I'm showing you one example of a posterior sample we inferred for each of the 5 objects in our sample. This is an edge-on view of the geometry, where the observer is looking from this direction along this axis. And these are sort of how the observer would see it. So sort of a face-on view from the observer's perspective. And so you can see, they're all quite disk-like, but they're all somewhat different. What we also found was that the results were consistent with preferential emission from the far side of the Broadline region, as you can see here, where the different sizes of the point particles correspond to how much emission is coming from each point.
Yeah. Thick disk.
Yeah.
I look at the second guy, that looks pretty thin to me.
Yeah, so the thinnest disk we found is approximately 10 degrees for the half opening angle. I mean, remember there'll be some uncertainty in this value, and so this may also, if this looks less than 10 degrees, although it doesn't look too off, that may be a thinner posterior
And the
sample.
velocity was circular, or what's the best fit?
For that one, let me get to it. I can't remember, I think that one may have had a bit of inflowing dynamics. But you can see that there's sort of preferential emission back towards the central ionizing source. And this is interesting because that is actually what photoionization models would predict would happen. But we hadn't told the data that they should be including this at all. Okay, and so when you add the constraints on geometry with the constraints on dynamics, we're able to measure the black hole mass to within 0.15 to 0.3 dex uncertainty. So that's a pretty good improvement over the 0.4 dex uncertainty that we might otherwise have had to assume. So we were encouraged, and I went ahead and started working with a number of wonderful people on trying to apply this technique to as many other objects as I could get my hands on, because the LAMP 2008 sample was very specifically chosen to fill in the low end of the M-sigma relation. So it does not have sort of a wide variety of AGN parameters, I guess. So I started working with Catherine Greer, who's currently a postdoc at Penn State. She did her graduate work with Brad Peterson at OSU. And as part of her thesis, she was part of this reverberation mapping campaign that we have now been modeling. And it's a little bit hard to see on the screen, but basically what we found in looking at 4 of her objects is still a completely consistent geometry of close to face-on thick disk, with even stronger preference for more emission back towards the central ionizing source. One of her objects is particularly interesting though, 3C120 here, because this also has a radiojet inclination angle measurement. And so we can compare that with our inclination angle measurement from the Broadline region, and it turns out that they agree exceedingly well. So basically it looks like things, at least in this one case, are fairly well aligned in the inner regions.
And that hole in the middle,
Yeah.
that guy, that seems to be quite different from the other 3.
Yeah, it
Is
very
that an unusual object?
Good question. I don't think it's particularly unusual. These all have fairly similar black holes, luminosities, accretion rates, etc. It sort of varies. They all have very similar dynamics as well. There's some amount of uncertainty as well in this inner region, and because these are just one posterior sample, the difference may not be as big as this one example shows. But yeah, I don't think this object is particularly strange.
It's roughly where dust sublimates, is it?
No, so the dust sublimation radius should be much farther
Much
out.
further out.
Yeah.
Because there was once a suggestion that that's the origin of the broad emission lines. That interior, the dust sublimates, so it doesn't protect the atoms, they get ionized.
Yeah.
But once dust forms, then you can emit those lines. But
Yeah.
it doesn't seem to be the case.
Yeah, I mean, I think in the objects where we have dust sublimation radii, they tend to be outside of the broadline region sizes that we measure. Yeah. Okay. So then, more recently, I've also been working with Michael Fosna, who's currently a graduate student at OSU, working with Brad Peterson on yet another reverberation mapping data set. And so we're going to be analyzing a couple objects for that, and one of the objects that I'm particularly interested in is NGC 2617, because this is one of these changing look quasars. That for those of you who've not heard of these, they're objects for which they were sort of in one type of accretion state and then dramatically changed the height of their broad emission lines over a short period of time. So something interesting seemed to be happening in the inner regions, the accretion disks, for instance, of these objects. So it'll be interesting to see how different this object seems. Okay, so what about the dynamics for these 10 objects at least? What we find is basically we only see inflow plus some amount of near circular elliptical orbits, with, you know, most of the objects showing at least some indication of some amount of radial inflowing orbit, which was not necessarily what we expected. It's not completely inconsistent, though, with what other sort of more simple diagnostics of the dynamics in these objects can tell us. There are various much more simple techniques that you can use to get a handle on just the dynamics. And so this is not something that we should be too surprised by, but you know, looking at this, it's not just gas in simple circular orbits around the black hole, which is something you might have hoped for if you're using this gas to measure black hole masses.
So when you say inflow,
Yeah.
is it at a good fraction of the Keplerian speed?
Yeah, so the way that our simple model is parameterized is that you can sort of have something that's in a circular tangential orbit, or tangential velocity orbit, or the sort of opposite of that would be a radial at the escape velocity orbit, given its current position, which is not a very, I would say, complicated or necessarily super realistic model. But it does allow us to reproduce a lot of complicated transfer function shapes, which is sort of another way of thinking about the data and what information they encode.
So when you say inflow,
Yeah.
you're saying it's inflowing at
But yeah.
kind of the escape
So
velocity.
it's not always, so the picture that we have is actually a little more complicated. So if you imagine that, okay, this is going to be the VR and V phi. We actually allow things to sort of go back and forth between totally radial and totally tangential orbits, and oftentimes things hang out in distributions around there, and they're not only at like one point. Typically, to try to like include as much I would say flexibility as possible, we allow for distributions of dynamical orbits. Yeah. Okay, but unlike the first 10 objects we looked at, we've now been looking at a new sample with Peter Williams, who's a grad student at UCLA, working with my graduate advisor, Tommaso Treu. And in the first 4 objects he's looked at, half of them have showed outflow dynamics, which is interesting from the perspective that Avi brought up before of if you have potential, you know, significant other forces going on, you might start to worry that your black hole mass measurements are not particularly robust. And so this is something that we are hoping to follow up with much more detailed outflow modeling for what's going on in the broadline region in these two systems. So, but it's exciting in the fact that, you know, there are a lot of different theories about where outflows are formed in the inner regions of AGN and how they, you know, interface with the host galaxy and carry mass away from the system potentially. So if we could try to figure out how to get a handle on the kind of outflows that go on, then this data set could be potentially very interesting for that. Okay, and you can see here, these are distributions of time delay across the emission line profile, which is sort of another way of looking at the data. And I just show these because you can sort of see similar structures in various simulations, for example, in hydrodynamical line-driven disk winds. which is something that we could compare them to. Yeah.
We know roughly the quantum density of gas producing these broad lines, right? Because there are, with cloudy, one can estimate.
Yeah.
And then you have velocity, so you can estimate m dot. You have geometry, velocity, and quantum densities. You can estimate the mass accretion rate if it's inflow. Does it match what you need to fuel the AGN?
So we have not actually done super detailed sort of going from the emission picture to the gas picture, because if you actually go to the full gas picture using something like cloudy, that actually has a lot of other constraints that it places on the geometry. And so one of the things I'd like to do is to work within that picture completely and then get things like what is the mass inflow rate when you sort of do everything self-consistently. Because I think right now I would never be sure how seriously to take that sort of calculation. Okay, so very quickly, in the last 2 minutes, I don't remember what time we started, let me just talk about the big picture briefly. Because, you know, I've shown you we could model the broadline region in individual sources with very high quality data in order to reduce black hole mass measurement uncertainties in those objects. But there are all of 60 reverberation mapped AGN, even if all of those objects had really high quality data, which they do not. So, you know, one big goal for this project is to see how these results actually influence our ability to measure black hole masses in all AGN, using these single epoch measurements that I talked about at the beginning, using this relationship between the size of the broadline region and the AGN luminosity. And one of the zeroth order things we can try to test is, do AGN actually lie on the same m-sigma relation as local galaxies? And so one of my, you know, here are only 5 points, but we could easily, within the next year, double or triple the number of points on this plot. And so I think that's one way where we can at least start testing the assumptions we've been making all along about how we're measuring AGN black hole masses. And there are a couple other things that we can do too. We can look at the broadline region and see if it changes when we go to really luminous AGN or quasars, and see if we see a lot more outflows, or something else that would change our, you know, assumption that black hole masses can be measured robustly. We can also try to measure an independent value for the mean value of F, or in even more detail, try to see whether F is correlated with any more easily measured properties of AGN or the broadline region. So one of the correlations that we found so far is between the value of this normalization factor F and the inclination angle of the broadline region, which makes sense because we keep finding these disk-like structures. And of course, if you look at that more John or more face-on, that's going to change the normalization factor that you would need.
Not by a factor of 30.
It can be by quite a lot. Yeah. So.
Does it go into the average value of F that you infer, though? Different inclinations would give you a different F and an average.
Yeah, so, okay, so if you're calculating an average value from all of these, then that uncertainty in the inclination angle is going to come into that. But, I mean, I think part of the idea is to see if you can maybe come up with a proxy for how to measure inclination angle. I mean, that's one of the tricky things with trying to understand how to get proxies for things that are very hard to measure. I mean, we have not had real inclination angle measurements of the broadline region before this. So we have not been able to test whether anything that's more easily measured can be used as a proxy for this. So now we can finally start testing these things.
Is there any reason why you can't use this broadline region method on the near universe objects that we already have good information about?
That's an excellent question.
And compare them?
Yeah, so there are only a couple cases that I'm aware of where you could do both reverberation mapping and one of the other methods. Unfortunately, the types of systems that are good for one generally make it bad for the other. Misty Bentz has been very actively looking at comparisons like this. I am not aware of super high quality reverberation mapping data on any of those sources though, and that's what you need in order to do this. So, yeah. But that would be a very good comparison. Okay, so because I don't want to keep you guys here too much past, let me just very, very quickly say that there are a lot of different reverberation mapping programs that are in the works or that have been recently completed that have sort of given a lot to our understanding of the broadline region. Everything from looking at both optical and UV lines At the same time, trying to look at, accretion disk physics using reverberation mapping, doing follow-up on targets we've already looked at to look for evolution in the broadline region, and starting to monitor much higher luminosity AGN in order to start to test whether AGN luminosity affects our ability to measure black hole masses. These are all things that we should be able to test either currently or in the very near future. And I'm also starting to work on trying to develop more realistic broadline region models so that we can connect what we see to actual physics of gas, test some of the assumptions that are typically made when, generating cloudy models, and also try to get some more understanding of the dynamics that are going on, especially in the outflowing objects. So just to conclude, I think the broadline region modeling approach is pretty powerful in that it gives us a lot of information that we didn't have before about quantitative constraints on broadline region structure, and finally really a way to measure AGN black hole masses more precisely than we could before. And we have a lot of different results in progress, and hopefully you'll be seeing them on the archive before too long, as well as some tests of different broadline region models. So thank you.
Questions for Anna?
So Anna, I might have asked you this before.
It's okay.
But I've forgotten. The broadline region, the old picture was that it's a zillion clouds just going round and round. But the picture that I have found more attractive is that it's really an outflowing wind. The wind being blown out of the disk, it's going out with some velocity like several thousand or 10,000 kilometers per second, so it gives you broad lines. Now that seems to be in conflict with your result that most of the objects actually have an inflow rather than an outflow. Are you actually disproving that model?
I don't think it's necessarily disproven at all, because I think what we're finding is, and not even just this method, but every way that you can look at reverberation mapping data using different methods has all found, in a lot of cases we require some amount of radial motion. And it's possible.
Radial inflow.
But radial motion period, right? Either inflow or outflow.
Okay.
So we found objects that have these preference for outflow, but you might also imagine that maybe gas cannot actually, or some of the gas can't escape from the sort of potential and comes and rains back down, and so maybe you see it, because you're only going to see it when it's actually able to emit broad lines. So maybe when it can emit broad lines is not when it's being launched, but maybe when it's coming back in. So I think this does not necessarily disprove that there are outflows. In fact, I think it's very likely that there are, because something is needed to give the gas its radial motion, and outflow seems like a perfectly good reason for that.
But you want a failed wind.
Or partially failed wind.
Partially failed wind,
Yeah.
but some conspiracy so that the broad lines only come from the failed part of the wind.
That's hard to imagine.
To me, because it's the
maybe
it's the line that's actually driving the wind.
Yeah. So, unless you're over-ionizing it early on.
Mm-hmm.
So I think what we really need to understand this fully is detailed simulations that actually tell us what the gas density is and where the emission is coming from in outflow simulations. And there are people working on this. So I was just at the KATP DISCS conference, and there were multiple talks about outflows launching out of winds and how it's very hard to do the full picture well, because you need radiative transfer to really understand the ionization state of the gas. And unless you know how ionized the gas is, you may or may not be able to generate emission lines from there. So it's sort of a very complicated problem, and I would love to have constraints on what should be going on from simulations.
Follow up, and there's no just a plain geometrical ambiguity between the inflow and the outflow. Not resolving it, so
it's because of the time delays. So that sort of breaks the symmetry. Yeah.
Our last question, Tom.
Yeah, so one interesting type of objects that you can discover, and I don't know if you've looked for them, are binary black hole systems, because if you have two black holes orbiting, then obviously the dynamics would be quite different. Did you check?
So we have not tried modeling any of these as binary black
No,
holes.
but did you see evidence for them?
So we have not found evidence that the simple model is doing a particularly bad job.
Okay.
It's very interesting though, because reverberation can have similar changes that you would see in a binary black hole situation. And so I think as time goes on, the reverberation mapping community and the binary black hole community could end up talking a lot more about the, you know, what the signatures that people are seeing actually mean.
We
and
wrote a
can,
paper about this
yeah,
with Yu Shen.
Yeah.
You can check it out.
So